All right, so this is question number 6 from the 2021 AP Calculus AB exam. It's another differential equation FRQ. So the situation we've got is that we've got medication being administered to a patient, and we have an amount in milligrams of that medication after t hours is the function y equals a of t. And it satisfies the differential equation dy dt equals 12 minus y over 3. And we're again given an initial condition that at t equals 0, there are 0 milligrams in the patient. So at t equals 0, a is also equal to 0. First off, they just give us a slope field, and they tell us to sketch the solution curve through the point 0, 0. So whenever they're asking you to sketch this solution curve through that point, just make sure that you first off include the point 0, 0, and then just generally follow the trajectories of those slopes, noting that we've got an asymptote right here, right, that we don't want to cross. So in order to get all the points, well, the one point for this, just basically follow the slopes there and make sure that it extends all the way to the far right and to the far left of the slope field, and that you don't cross that asymptote. And that's just worth 1 point here for part A. Pretty straightforward for part A. For part B, they ask us using correct units to interpret the statement that the limit as t approaches infinity of a of t is equal to 12. So this requires just a sentence explanation. And note that they do say using correct units. So if you don't put the right units, then you're not going to get the point. So we need to say something like, maybe something like, as time goes on, or as time goes, as this medication is entering the patient, we would say that the amount of medication in the patient, because that's what's happening here, right, is we're administering a medication to the patient, and they want to see those specific words, right, amount of medication in the patient, is approaching 12 milligrams or is getting close to 12 milligrams. And they want some wording just like that, that indicates that the amount is getting close to 12 milligrams, but not that it equals 12 milligrams. If it says it gets to be 12 milligrams, then you're not interpreting that correctly, right? And so that's what's happening here, is we're saying that as time goes on, the amount of medication the patient is getting close to 12. Doesn't necessarily get to 12, but it's approaching 12, right? We have to have that keyword of approaches, or gets close to, or is nearing 12 milligrams, because that's what a limit is, right? A limit is not the amount that you actually get to necessarily, even though sometimes we do get there, right? That's not what a limit is. The limit is the value you are approaching. So that's what the keyword we're looking for here is. And again, that's just worth 1 point for part B. For part C, they now ask you to use separation of variables to find y equals a of t, which is the particular solution to this differential equation, with the initial condition that when t is 0, a is 0. So we'll separate the variables. That's always step 1 here. So we have dy over 12 minus y equals 1/3 dt. And just doing that right there is going to be worth 1 point. We'll give ourselves 1 point here for that. And then next step is we'll actually integrate it here. So the integral of 12 minus y, that's a u substitution, right, where u is 12 minus y, and du is negative dy. So we'll put in a negative and a negative, which ends up making this just turn into the integral of the opposite of du over u. So it's just negative natural log absolute value 12 minus y plus a constant that we won't bother to write because we're going to subtract it to the other side. And on the other side, we get 1/3 of t plus some constant. And so you get 1 point here on this problem for correctly anti-differentiating both sides. You'll get another point if you solve for the constant and plug it back in. So let's do that. When t equals 0, we get negative ln of 12 on this side equals c. So this is pretty straightforward to get our constant of negative ln 12. And then what you might see in the scoring guidelines is that they solve for y first and then find the constant, but there's no reason that you have to do that. I think it's always easier to solve for the constant right away and then solve for y afterwards. So as I plug that back in, we're going to end up with negative natural log absolute value 12 minus y is equal to 1/3 t minus the natural log 12. And that's going to be our third point here for this problem, for actually plugging that constant back in. Okay. And then to earn our last point, we just need to finish solving for y. And so we'll start off by just dividing by a negative. So we'll get natural log absolute value 12 minus y is equal to natural log 12 minus 1/3 t. Just distribute a minus sign through it, flips the signs of both of those. Then we'll exponentiate both sides. Remembering that when we have something like e to the ln of a, we don't even need it to be ln. We'll deal with the ln in a second. When we have e to the a minus b, that can be written in one of two ways. It can be written as e to the a over e to the b, or it could be written as e to the a times e to the negative b. Okay? And so I'm going to rewrite this as e to the ln 12 times e to the negative 1/3 t, which is going to let me turn e to the ln 12 into just 12. So we have 12 e to the negative 1/3 t now. And on this side, we'll clear off the absolute value by putting in a plus or a minus here. And we have to indicate which one it actually is. We know that if we plug in 0 for y, we need to get 0 for t. So if I put in both of those, right, we're going to have 12 minus 0 equals plus or minus 12e to the 0. Well, that clearly indicates that it needs to be the positive 12e to the negative 1/3 t. So what we've got now is 12 minus y equals positive 12e to the negative 1/3 t. We can then just add y to both sides and then subtract the 12e to the negative 1/3 t to the other. So we'll say y equals 12 minus 12e to the negative 1/3 t. And that's our final answer for part C. And that's worth a 4th point there for part C. So 4 total points in part C, with 1 in part A, 1 in part B. That's 6 total, which means that part D is going to be worth 3 points for us here. And strangely enough, usually the separation of variables part of the differential equation is the end of it, but in this case, they've got a part D for us here. So we have a new procedure that's going to be used to administer this medication that's going to be modeled by a function b of t that has a different differential equation, dy dt equals 3 minus y over t plus 2. And it says at t equals 1 hour, we've got 2.5 milligrams of medication in the patient. And we want to know, is the rate of change of the amount of medication in the second patient increasing or decreasing? And so this is where you've kind of got to be careful about the wording. So if b of t, right, b of t represents the amount, then dy dt, or b prime, represents the rate of change of the amount. Well, what we want to know is not is the amount of the medication increasing or decreasing, but is the rate of change of the amount of the medication increasing or decreasing. So we want to know, is dy dt, or is b prime, increasing or decreasing? And so in order to figure out if something is increasing or decreasing, you need to take its derivative. So what we need is the derivative with respect to t of 3 minus y over t plus 2. In order to do that, we'll have to use the quotient rule and some implicit differentiation here. So the derivative of the 3 just goes away. The negative sign can just kind of sit out front. And then we're going to do the quotient rule on y over t plus 2. So that'll be the denominator, t plus 2, times the derivative of the numerator with respect to t, which is dy dt, and then minus the numerator times the derivative of the denominator, which is just 1, all over the denominator squared. So we're looking at this value here, negative of t plus 2 times dy dt minus y times 1 over t plus 2 squared. And they gave you 1 point here for correctly using the quotient rule. So there's 1 point. Now, it doesn't specifically say to write the second derivative in terms of y and t, but it might be useful for us to replace that dy dt with what dy dt is actually equal to, 3 minus y over t plus 2, or at least with the value, right? So we know that when t is 1, we have 2.5 milligrams of the medication. So when t is 1, y is going to equal 2.5. So if we just well, not y is going to equal 2.5, but yeah, the b value is going to be equal 2.5, which is the same as 1. So what we'll do is we'll plug in 1 and 2.5 into this entire thing. So for all of the t's, we're going to put in a 1. So we're going to start with a negative, right, because we have that negative out in front. And then t plus 2 is going to be 1 plus 2. And then the 2.5 needs to go in for the y into our dy dt, right? And so our new dy dt looks like this. So it looks like 3 minus 2.5 over t plus 2, which we already know t plus 2 is 3. So we have 1 plus 2, or 3, times 3 minus 2.5 over 3. And then we have minus our y value times 1, so that's going to be minus 2.5. And then it's all over 1 plus 2 squared. And so what we'll do is we'll just simplify this down here. So 1 plus 2 is 3, and 3 times 3 is going to be 9. So we're going to have our negative out in front. We're going to have 9 minus 3 times 2.5 over 3. It's just going to be 2.5. And then minus another 2.5. And then it's all going to be over 3 squared, which is 9. So what we've got is 9 minus 2.5 minus 2.5, in other words, 9 minus 5, which is 4, over 9. And with a negative sign, of course, out in front. And so what we end up with is that our second derivative is equal to negative 4/9, which we know is less than 0. And if it's less than 0, that means that, we took the derivative here and evaluated it to see its sign, right? That means that dy dt is decreasing because the second derivative is less than 0 at t equals 1. Okay. And so we get 1 point for showing that the sign here was negative, and we get 1 point here for indicating that dy dt is decreasing. And what we'd really want to do is not just say dy dt here, but we'd want to say the rate of change in the amount of medication in the patient is decreasing at that time. And so we'd say, because the second derivative is negative at t equals 1. And that would give us our last 3 points there for this differential equation FRQ from 2021, problem number 6. And that is it for this problem. All right, so this is question number 5 from the 2022 AP Calculus AB exam. It's another differential equation question. And so part A here is just asking us to sketch a portion of a solution curve that goes to the point 1, 2, given this slope field that we have. And so they've been doing this a lot recently, and it's pretty straightforward. Just kind of follow the trajectories of the slopes. Make sure you kind of, flatten out and then get steeper again. And then do the same thing here, flatten out, go back up, flatten out, go back down. And if your solution curve looks, about like that, then you're going to get the singular point that is for this question, right? You just got to make sure that you need to get pretty much to the left and the right hand ends of the slope field, and that you don't have anything like, you don't do something like this, something ridiculous. Right? Just kind of generally follow what those slopes look like, and you'll be fine. Right? So there's part A, 1 point for part A. For part B, they're asking you to write the equation of the line tangent to the solution curve. Right? So the solution curve is y, right? Or the function f of x. And we want to write the tangent line to it at the point 1, 2. Well, that's nice enough that they give us the point. That's convenient. And then they want us to approximate f of 0.8 using that tangent line. Well, in order to write the equation of the tangent line, we need to have a slope and a point. And we just have the point. Luckily, we have the differential equation, which will tell us what the slope of the tangent line is, right? Because dy dx is going to be the slope of the tangent line to f of x. So just evaluate dy dx at the point 1, 2. Right? And so if I plug in 1 for x and 2 for y, we end up with 1/2 of the sine of pi over 2 times the square root of 2 plus 7, which is just 9. Well, the sine of pi over 2 is 1, so this just comes out to be 3/2. And so you don't get any points just for getting 3/2, but you do get a point for the tangent line equation. And I'll use point slope form here. Y minus 2, because we're using the point 1, 2, is equal to 3/2 times x minus 1. And you'll find in the scoring guidelines that they usually add the 2 back over to the right-hand side, but you can just leave it in point slope form. There's no reason to add that 2 over, other than you'll have to do it when you do the approximation for f of 0.8. But this answer is perfectly acceptable to get you the first point for part B. To get the second point for part B, you just need to plug in 0.8 for x. So we have y minus 2 equals 3/2 of 0.8 minus 1. Right? And so, 0.8 minus 1 is going to be negative 0.2. So we've got y equals 2 plus 3/2 of negative 0.2, right? This is negative 0.2. Negative 0.2 is the same as negative 1/5, right? So I have 3/2 times negative 1/5. Or in other words, what we have here is we have 2 minus 3/10. And so you could either give an answer of 17/10, or you could call it 1.7. Any of that's fine. And that would be our answer to get our second point there for part B. That's our approximation of f of 0.8 using the tangent line. And really common here is for them to ask us if our tangent line approximation is an under or an over estimate. And so the easiest way for us to do this is to determine whether the function is concave up or concave down on this interval, right? And so remember that if the function is concave up, a tangent line is going to be an underestimate, and if the function is concave down, a tangent line is going to be an overestimate, right? That tangent line is above the concave down function, and it is below the concave up function, right? So we know that it says that f double prime of x is greater than or equal to 0 on this interval from -1 to 1, right? And so, well, we don't actually have to do any work here. All we have to do is just kind of make an analysis of this. Say, well, if f double prime of x is greater than 0, then f is concave up. And if f is concave up, then that means that the tangent line is an underestimate. And that would be sufficient for you to get the 1 point that you get for this part. So tangent line is an underestimate, and that would be good enough. And make sure you indicate that f double prime tells us that it's concave up. And for our last point here, or for our last part here, we've got the exceptionally common use separation of variables to solve this differential equation with the particular condition that f of 1 is 2. And so they don't always tell you to use separation of variables, but that's pretty much what you always need to use. So we'll do that. We'll do dy over root y plus 7 is equal to 1/2 sine pi over 2x dx. And that's the separating the variables part. That's worth 1 point, right? You're bringing the y stuff over to the left-hand side and the dx over to the right-hand side. And they give you 1 point just for separating the variables. Now, in this one, they're going to give you 1 point each for the two different antiderivatives because they're both, a little bit more difficult. Right? So for the first one here, right, when we integrate 1 over root y plus 7, well, we can think about that as, u is equal to y plus 7, and du is just dy. So it's a pretty basic u sub. Really what we're doing is an integral of u to the negative 1/2 du, which is 2 root u, or 2 root y plus 7. And of course, there's a constant that gets added to that, but because we're going to have another integral on the other side that's going to also have a constant added to it, and I have a constant on each side, I can subtract one from the other and just be left with a singular constant on one side, and I'll leave it on the right-hand side. So 1 point here for this correct antiderivative. And now we'll do the other antiderivative, which is also going to require a substitution. We'll say, let's let v equal pi over 2, then dv is, pi over 2x, then dv will just be pi over 2 dx, which we don't have. We have a 1/2 there. We have the half, but not the pi over 2. So we'll multiply by pi here and by 1 over pi out in the front. So really, effectively, what we've got is an integral with 1 over pi out in front of the sine of v dv. And that integral should then just become negative cosine v with the 1 over pi out in front. So negative 1 over pi cosine v, or cosine pi over 2x, plus the constant. And so that's worth another point. So there's our third point. To get the fourth point, you need to solve for the constant and plug it back in. So to solve for the constant, we're just going to use our initial condition that when x is 1, y is 2. So we have 2 root 9, if y is 2, is equal to negative 1 over pi cosine of pi over 2, because x is 1, plus our constant. Well, the cosine of pi over 2 is just 0, so we end up with a constant of 6. And then to get that next point here, that fourth point, we're going to rewrite this as 2 root y plus 7 equals negative 1 over pi cosine pi over 2x plus 6. Right? And that gets us our fourth point here. And then our fifth point just comes from solving for y, which in this case should be pretty straightforward. First, we're going to divide everything by 2. Right? So if I divide everything by 2, we're going to have negative 1 over 2 pi cosine pi over 2x plus 3. Then we're going to square everything. So we'll have y plus 7 equals all of that. It's not a plus there. We got to have a cosine there. Cosine pi over 2x plus 3. All being squared, and then we'll just subtract 7. So our final answer is y equals negative 1 over 2 pi cosine pi over 2x plus 3, all squared, minus 7. And that would get you your fifth and final point for part D. Right, so that gives us 9 total points for this FRQ. And that is all you need to do to get all the points on that differential equation free response question. All right, so here we're looking at question number 3 from the 2023 AP Calculus AB exam. This is another one of the ones that I consider differential equation FRQs because you're given a differential equation, right? And so what we've got is a situation where we have a bottle of milk being taken out of a refrigerator and being warmed up, right? And so we've got an increasing function m, right? So they've told us that m is increasing. That's going to model the temperature of this milk given this differential equation, right? T is measured in number of minutes since the bottle was placed in the pan to warm up, and the m is measured in degrees Celsius, right? And it says at time t equals 0, the temperature of the milk is 5 degrees Celsius, and it can be shown that the temperature is always less than 40 for all values of t, right? So the first part of this is just to sketch the solution curve to the slope field that's given through the point 0, 5. So this is pretty straightforward. Just note that right here, and you don't need to write this, but this is an asymptote, and this is the value at which our milk can't get more than 40 degrees Celsius, and that's that line, that's that restricting line there that we can't go above. So when you sketch your solution curve, follow the trajectories of these slopes, but just make sure that you do not go above that line at 40, right? That you want to be approaching it, getting closer to it, but not actually touching. And as long as your line pretty much follows those slopes, you should be perfectly good to get the point for this one. And you have to be completely below that horizontal line at y equals 40, right? And it needs to go through the point 0, 5, and you need to get to the left and the right ends, or at least pretty darn close to them to get that point. So there's 1 point there for part A, fairly straightforward. For part B, we're going to use the line tangent to the graph of m at t equals 0 to approximate m of 2. So we're writing a tangent line equation here. And so whenever we write a tangent line equation, we know that we need to find both the slope and we need to find some point, right? We can't write the tangent line equation without a slope and a point. Well, if we're writing the equation of the tangent line at t equals 0, we are given the point that when t is 0, the value of m is 5. So the point that we're going to use here for this is going to be the point 0, comma, 5. And our slope, right? Our slope is just going to come directly from dm dt evaluated at that point. Well, dm dt is 1/4 of 40 minus m. So that'll be 1/4 of 40 minus 5, which is 35 over 4. So we're getting 1 point here for just finding this slope. Right? So we got 1 point here for finding the slope. And then we get a second point for actually writing the equation of the tangent line and then using it to approximate m of 2. So we can write this tangent line as y equals, and since this is already a y-intercept, effectively, right, at the point 0,5, we can just do this in slope-intercept form. We can just say it's 35/4 t plus 5. Or if you choose to write point-slope form, that's fine. A lot of these ones, as we'll see as you watch more of these videos, end up giving you a point that's not the y-intercept, so you have to use point-slope form. But this one's a y-intercept, so we'll just use slope-intercept form. All we have to do is then plug in 2 for t here. So to find y of 2, we just do 35/4 times 2 plus 5, which is 35/2 plus 5, which just comes out to be 22.5 degrees Celsius. And that is our approximation, and that is worth the second point here for this FRQ. Make sure you show all of this work as you go through and do the process. All right, for part C, it tells us to write an expression for the second derivative of m with respect to t, and then to use that to determine if our answer from part B was an under or an overestimate of the actual value. So in order to find the second derivative with respect to t, we just need to take the derivative with respect to t of 1/4 of 40 minus m. And it's become pretty common for them to ask about the second derivative here in terms of t of something that doesn't even have a t in it, that only has the other variable. So we have to remember that when we do that, first of all, the 1/4 just stays as is, and we take the derivative of 40 minus m. Well, the derivative of 40 is 0, and the derivative of negative m with respect to t is negative dm dt. And so what we need to do is we need to then replace the dm dt with what dm dt equals, because it says to write this in terms of m, and having it as dm dt is not in terms of m. So what we've got is negative 1/4 of dm dt. So negative 1/4 of 1/4 of 40 minus m. Or in other words, negative 1/16 of 40 minus m. And so this is worth 1 point here on this question, right? That is our expression for the value of the second derivative of m with respect to t. And then we have to determine if it's an over or an underestimate. Well, we used a tangent line to approximate this. So what we need to remember is that if we use a tangent line on something that is concave up, that was supposed to be actually tangent to it, a tangent line, almost made it that time, solve this the easy way, there we go, a tangent line on something that is concave up, then we can see that the tangent line is under the function. And if we have a function that's concave down, then the tangent line is going to be above. It's going to be an overestimate. So all we need to do is we need to determine if the function is concave up or concave down. Well, that entirely relies on the second derivative. So we'll just plug in our value for m that we have here. Well, we know that, we don't actually have a specific value for m that we need to test. We need to make sure it's true on the entire interval that we're talking about. And we know that for this entire, I forgot my negative sign over here. So let's fix that, because that's going to really mess up this answer. Right, we had negative 1/16 of 40 minus m, not 1/16 of 40 minus m. And if you want to get that point, make sure you don't lose the negative sign like I did. What we've got here is we know that m is always less than 40. And if m is always less than 40, right, if m is less than 40, then 40 minus m is going to be greater than 0. So what we've got here is we've got negative 1/16 times something that is greater than 0, times a positive number, which is certainly going to be less than 0. So what we'll note is that for m less than 40, the second derivative is going to be less than 0. So m is concave down. And the tangent line, when we're concave down, we look at our little picture, the tangent line is going to be an overestimate. And so that is our answer here. That is our reasoning with the work shown to back it up. It's an overestimate. We've got our reasoning, and that's worth 1 more point. So that's now up to 5 points for this problem. And for part D here, the very common part, or the last part of the differential equation FRQs, is to separate the variables and solve. And so we'll just get right to it. To separate the variables, we're going to divide by 40 minus m. So we're going to have dm over 40 minus m is equal to 1/4 dt. We'll bring the 40 minus m to the left with the dm and the dt over to the right-hand side. They give you 1 point right off the bat every time for just properly separating the variables. That should be an easy point. Then you integrate both sides. This time you needed to get both antiderivatives here to get your second point here. Sometimes it's worth 1 point for each of them, but not in this case because the right-hand side, 1/4 t plus a constant, is just really easy. So for this one, you're going to use a u substitution here. U is going to be 40 minus m, and du will be negative dm. So really, we want to put a negative and a negative here, which makes this negative integral du over u, or negative natural log absolute value of 40 minus m. And that side's got a constant too, but we can always subtract the constant over to the other side and just be left with one constant on one side. So this is worth our second point here if we correctly anti-differentiated both of those. Next thing we want to do is we want to solve for our constant. Well, our initial condition is that when t is 0, m is 5. So we have negative natural log of 40 minus 5 is just 35 is equal to 0 plus c. So our constant is just negative ln of 35. And so we'll then go back in to our original solution here. We'll just take this constant and plug it back in. So we've got negative natural log absolute value of 40 minus m is equal to 1/4 t minus the natural log of 35. And once we plug that back in, that earns us our third point there. And we can earn our fourth and final point for this by actually solving for m correctly. So first we'll just divide by a negative sign. We have natural log absolute value 40 minus m is equal to ln 35 minus 1/4 t. We'll exponentiate both sides. In other words, we'll raise both sides as powers of e. And as we do that, we'll end up with an absolute value of 40 minus m is equal to, and over here, we have e to the a minus b, or e to the a plus negative b, which could be written as, right, e to the a, e to the negative b, right, if we have two things that are being added together. And so this can be written as e to the ln 35 e to the negative 1/4 t. And we know that e to the ln of 35 is just 35. And so we have 35e to the negative 1/4 t. And we'll clear off the absolute values here by putting a plus or a minus. So we have 40 minus m is plus or minus 35e to the negative 1/4 t. Now, We could have just cleared off those absolute values earlier, knowing that m is always less than 40, and if m is always less than 40, then the thing inside the absolute value is always positive. Right? But I think it's good for us to see what happens when we clear them off with the plus or minus and like just test out our values in the end. So we know that when we plug in 0, we need to get 5. Well, if I plug in 0 right now for t, I'm going to get plus or minus. If we test, I'm going to write this here, test the 0.05, I'm going to get 40 minus 5 equals plus or minus 35. Well, the answer is it's going to equal the plus 35. And so I don't need the minus sign here. I don't need the plus sign either. I'll just put a 35e to the negative 1/4 t. Right? So this is just our little test off to the side. And now we can finish off the problem here. Should be pretty straightforward. I'll just add m over to this side and subtract this over, which is going to yield my final answer here, which is going to be m is equal to, we'll have 40 minus 35e to the negative 1/4 t, right? If we add m to the right and then subtract the 35e to the negative 1/4 t, we just get m equals 40 minus 35e to the negative 1/4 t. And getting all the way to there is your final point for that FRQ. And so 4 points in part D to get us to the total of 9 points for this free response question. And that's it for this question. All right, here we're looking at question number 3 from the 2024 AP Calculus AB exam. This problem here is what I call a differential equation FRQ, where they're giving us a differential equation dh dt equal to 1/2 of h minus 1 times the cosine of t over 2. Then they give us some other information about the units. You know, h of t is in feet, t is in hours. And we know that h of 0 is equal to 4. And they'll often give us some initial condition that you'll probably have to use somewhere along the line. So part A here is probably the easiest part of this question for this one. It just says we've got a portion of the slope field for the differential equation, and they want us to sketch the solution curve, which we're calling y equals h of t, that goes to the point 0.04. They've already given us the point 0.04, so all we have to do is just generally follow the correct slopes here. So this is just going to go, up following these slopes and then kind of flatten out and then come back down. And if you have something about like that on your paper, then that's perfectly fine. There's nothing wrong with that at all. They just give you 1 point for correctly drawing this slope field, so this part is worth 1 point. Just make sure that you extend your solution curve all the way from the left-hand side to the right-hand side here. Because if you don't go far enough on one side or the other, they're not going to give you that point. And no need to do anything beyond what's shown in the slope field. They're not going to even look at what's outside of it. So that's part A, 1 point for part A. For part B here, I've recopied the question again, so we've still got the same beginning part here, but it says for 0 to 5 for t, it can be shown that h of t is greater than 1. And we want to find the value of t at which h has a critical point. So note that we're saying find the value of t at which h has a critical point, which means that we might be looking up here to see when our derivative is equal to 0 and noting that h equals 1. But that's not what they're looking for. And first of all, we know that on our interval, h of t is always greater than 1 anyway, right? So h can't equal 1. So then we have to determine if that critical point is a maximum, a minimum, or neither, and then justify our answer. So what we're asked to do is find that critical point. Well, a critical point is when the derivative is 0 or when the derivative is undefined. So nothing in this differential equation here could ever cause it to be undefined. No real numbers plugged into that will ever make it undefined. So really all we're looking at is what makes it 0. And we've already established that since h of t is greater than 1, we know that there's no values of h that are going to make it 0. Right? And so we really just need to look at the cosine of t over 2. And we want that to equal 0. So that's how we're going to find our critical point. And so we know that cosine is equal to 0 whenever the angle is pi over 2 plus pi n. Right? As every pi, we end up equaling 0 for cosine, right? Cosine of pi over 2 is 0. The cosine of 3 pi over 2 and 5 pi over 2 and so on is equal to 0. And so then what we'll do is we'll just solve for t. So we'll multiply by 2. So we get t equals pi plus 2 pi n. And so then we'll want to note that we're looking at the interval for t from 0 to 5. Well, the only option here is when n is 0, we're going to get t is equal to pi. And that's going to be our critical value. Right? If I tried to do n equals 1, we'd already be at 3 pi, which is way outside this interval. And if we did negative 1 for n, we'd have pi minus 2 pi. That'd be negative pi, and that's outside of the intervals from 0 to 5 also. So we've found our critical point. Okay? And then what we need to do is determine if it's a maximum or a minimum. And that has to do with whether this function goes from increasing to decreasing at this point or decreasing to increasing at this point, or whether it does neither of those things. And so there are a couple of different ways we can check this. One of the ways is we can make a sign chart here and say, all right, here's 0, the t-value of 0, and the t-value of 5 here. And then somewhere in the middle here is the t-value of pi. And we can then say this is, we always want to indicate this is a sign chart for dh dt, right? Just so that we don't get confused about what we're making a sign chart for. And then we can just test a value of t between 0 and pi, and a value between pi and 5, and see if the derivative is positive or negative on that interval. And so if we take something between 0 and pi, like let's say we plugged in pi over 2, right? Well, if I plugged in pi over 2, we'd get the cosine of pi over 2 divided by 2 as the cosine t over 2 part, right? Which is the cosine of pi over 4, which we know is greater than 0. And we also know that 1/2 of h minus 1 is greater than 0 because we know that h is greater than 1. So we know that on this interval, dh dt is positive, which tells us that h, the h of t function, is increasing on that interval. And then if we test something between pi and 5, right, we can note that if we do that, let's say we did 3 pi over 2, right? The cosine, right, and again, we know that the 1/2 of the h minus 1 is positive still. So if we do cosine of 3 pi over 2 divided by 2, that'd be the cosine of 3 pi over 4. Well, 3 pi over 4 is in the second quadrant, right? And in the second quadrant, cosine is always negative. Therefore, we know that our derivative is negative on this interval, which means that h is decreasing. And so that tells us that we have a relative maximum at this critical value of t equals pi. And so we'd write over here that we have a relative maximum at t equals pi. And you'd have to give a reason for this, right? It does say justify your answer, and our justification can't just be a sign chart that's drawn. We need to say there's a relative maximum at t equals pi because dh dt is greater than 0 on the interval from t equals 0 to t equals pi, and dh dt is less than 0 on t equals pi to t equals 5. And so that would be our justification for this. And so the way the points are broken down for this one, they're going to give you 1 point for finding the critical value. They're going to give you 1 point for even attempting to consider the sign of dH dt, and they're going to give you 1 point for the correct answer with a worked out solution. Now, if you didn't think about using a sign chart, that's okay. There's other ways to do this problem, to do the second part of it. We can also take a second derivative of this, because we know that our derivative is equal to 0 at t equals pi. And so let me go ahead and on a new page here, let's rewrite our dH dt. Right, dH dt was equal to 1/2 of h minus 1 times the cosine of t over 2. And we have this thing, right, called the second derivative test. The second derivative test says that at a place where the first derivative is equal to 0 and the second derivative is positive, then we have a relative min. And if the second derivative is negative, then we have a relative max. That's our second derivative test. It only works when the derivative is equal to 0. It doesn't work for places when the derivative is undefined, but it is another option that we can use here. And so if you feel more comfortable taking a second derivative, you can do that. You just need to make sure you do it using the product rule here. So I'm going to keep the 1/2 out in front for the whole thing, because that's not going to affect anything. But then I'll take my derivative, and I'll keep the h minus 1 to start, and I'll take the derivative of cosine t over 2. Right? And using the chain rule, the derivative of cosine t over 2 is negative 1/2 of sine of t over 2. And then we'll add to that the second part of our function, the cosine of t over 2, times the derivative of h minus 1. Well, the derivative of h minus 1 is just dH dt. And so this is our second derivative. And if we go in here and kind of continue working with this, right, what we've got is h minus 1 times negative 1/2 sine t over 2 plus the cosine of t over 2 times dH dt, which was 1/2 of h minus 1 times the cosine of t over 2. And if we evaluate this when t is equal to pi, right, because that's the point we're looking at t equals pi, we've got 1/2 of, well, if t is equal to pi, then we've got h minus 1, and then the sine of pi over 2 right here is equal to 1, so we have times negative 1/2, if we just have the negative 1/2 times the 1. And then we have plus the cosine of pi over 2, and we know that the cosine of pi over 2 is equal to 0. So this whole term is just going to equal 0. And so now we can see that this is just negative 1/4 of h minus 1. And we knew that h was always greater than 1, so we know that h minus 1 is always positive. So negative 1/4 of it is less than 0. And so we would indicate that at a place where the derivative was equal to 0, the second derivative was less than 0, and therefore we'd have a relative max, which is exactly what we got using the other method. So either one of these is a perfectly viable option. You'll get all the points for the problem as long as you show all the work and give a good explanation. So either way is good. All right, for part C here, and this is the part that is almost always in the differential equation FRQs, it'll tell you to solve the differential equation. Right? It says, in this case, it even tells you use separation of variables. Now, sometimes it doesn't actually say that, even though it is almost always a separable differential equation. And solving a separable differential equation is almost always the highest point value of any problem on the AP test, right? Sometimes these are worth 5 or even 6 points. This one happens to be worth 5 points. So most of the other parts of FRQs are not worth that much. So we'll use our separation of variables to start with, and that's worth a point right off the bat, just separating the variables. So if you don't even know what to do beyond that, just separate them. Keep your dh on the left and divide by your h minus 1. And then keep your 1/2 over here if you want to. You could bring it to the other side. It doesn't really matter, but we'll leave it on that side. And then just bring your dt to the right-hand side. So that right there is already worth 1 point. Okay? And there's no reason anybody should not get that singular point. That's 1 point for just doing that. For this particular one, they gave you a point for each of your antiderivatives. So if you take the antiderivative correctly of both sides of this, you're getting 2 more points. Okay? So the integral of dh over h minus 1, that's one of those simple u substitutions, right? Where u is equal to h minus 1 and du is just equal to dh. So it just is like integrating du over u, which is just natural log absolute value of u. So we have natural log absolute value of h minus 1. We could put a plus c there, but because we're going to have a plus c on the other side, we don't really need it. We could just combine the two constants onto just the right-hand side. So we've got natural log absolute value h minus 1. And then on the other side, it's another little fairly simple u substitution, right? If you let u equal t over 2, then du is just 1/2 dt. And really, we shouldn't use u here even though we didn't really write it out. We'll call it v since we already used u for the h minus 1. And so if I look at that, really this just becomes the integral of cosine v dv. And the integral of cosine of v, we know, is just sine of v. So this is just the sine of t over 2 plus that constant. And so just by doing the separation and the integration, that's a second point here, and that's a third point here for this problem. Sometimes they don't give you a point for each antiderivative. If one of them is a really easy one, they usually don't. But that's fine. And so the next thing to do here is to solve for the constant, remembering that they have given you an initial condition here, right? They said that h of 0 is equal to 4. So if I plug in 0 for t, I need to get 4 for h. In other words, I need to do natural log of the absolute value of 4 minus 1 is equal to the sine of 0 plus a constant. Well, this is just the natural log of 3, and the sine of 0 is 0, so that side is just a constant. So we've got a constant of the natural log of 3. Okay? And so that's worth a 4th point here for us, right? Almost. We have to actually plug that back in. So in order to get the 4th point, I think we need to just throw that constant in here. And we'll note that given in the problem, it told us that h was always greater than 1, right? And so we can just sort of eliminate our absolute, we'll actually show the steps of eliminating. We can eliminate that absolute value, but we'll show the steps on it. So what we've got here is we'll kind of box this off a little here, make this a little more clear. We've got natural log absolute value of h minus 1 is equal to the sine of t over 2 plus the natural log of 3. And in order to solve this for h, which is what we're asked to do, we're going to have to exponentiate it, right? Which means that we're going to raise this so that each side is a power of e, giving us an absolute value of h minus 1 is equal to e to the sine of t over 2 plus ln 3. Well, we know that e to the a plus b is equal to e to the a times e to the b. So I'm going to do that here. I'm going to say this is e to the sine t over 2 times e to the natural log of 3, which is going to allow me to rewrite this now as 3e to the sine of t over 2. And again, oh, sorry, I forgot to mention, this is our fourth point right here for plugging it back in with the constant. And so now we've got the absolute value of h minus 1 is 3e to the sine t over 2. Well, to clear off the absolute value, technically we should put in a plus or a minus here and get h, or h of t, is equal to 1 plus or minus 3e to the sine of t over 2. But of course, we can't leave both of those answers, right? We can only choose one of those two answers. And so what we have to do is we have to make sure that our answer that we provide satisfies our initial condition that we had up here, that h of 0 is 4, right? And so if I try to solve that, I get 4 equals 1 plus or minus 3e to the sine of 0, which is just 0. Well, we can see that 4 equals 1 plus or minus 3 tells me that I can't have the minus 3. I need to have the plus 3. And so we can eliminate this minus sign here and say that our final answer is h of t is equal to 1 plus 3e to the sine of t over 2. And that is our fifth point for that part. And so that totals up the full 9 points of the problem. We got 1 point for part A, we got 3 points for part B, and we ended up with 5 points here for part C. And that is about all there is to say about this particular differential equation FRQ.